On which side of the screen do you think is work being done? Work is being done only on the left side of the screen, where we see that a block is being pushed across the floor. Even though in the second case, the wooden crate is being pushed, there is no work being done. This is because, in physics, work is said to be done only when an applied force succeeds in moving a body. Consider a wooden block which is at rest on a horizontal surface. When the block is pulled by an external horizontal force F, it is put into motion and is displaced through a certain distance d, and we say work is done on the block. Let's consider a second case, where the direction of the force is not along the direction of the motion of the block. Here, the force makes an acute angle theta with the horizontal. In this case, too, we observe that the block moves in the horizontal direction only. Here, the total amount of force is not being utilized to move the block. Only the component of the applied force along the direction of the displacement is responsible for the motion of the block. This component is F cos theta. Thus, here, the work done on the block by the force is the product of F cos theta and displacement. In this expression for the work done, both F and D are vectors, whereas the product, work done, is a scalar. Thus, this quantity Fd cos theta is called the scalar product of the two vectors F and D. In vector form, it is denoted by a dot in between the two as shown, and is read as F dot D. Hence, it is also referred to as the dot product. Now let's understand dot product in detail. The dot product of two vectors A and B is equal to the product of the magnitude of the two vectors and cosine of the angle between the two vectors. The result of a dot product is always a scalar. Now, let's see some properties of the dot product of vectors. 1. The dot product of vectors is always a scalar quantity. 2. The dot product is commutative. Consider the two vectors A and B inclined as shown. Theta is the angle between the two vectors. The component of one vector in the direction of the other is called the projection of the vector on the other vector, and is denoted by the product of the magnitude of the vector and the cosine of the angle between them. Hence, we see that B cos theta is the projection of vector B on vector A. So, the dot product of vectors A and B can be written as A into B cos theta, which is equal to AB cos theta. Let this be equation 1. Similarly, we see that A cos theta is the projection of vector A on vector B. So, the dot product of vectors A and B can be written as B into A cos theta, which is equal to AB cos theta. Let this be equation 2. From equations 1 and 2, we see that A dot B is equal to B dot A, which is equal to AB cos theta. Thus, the dot product of two vectors is commutative. The dot product obeys the distributive law. So, A dot B plus C is equal to A dot B plus A dot C. All dot products obey the rule M times A dot N times B is equal to Mn times A dot B, where M and N are just constants. Consider the unit vectors along the Cartesian coordinate axis I, J, and K. The angle between any two vectors in the same direction is 0. Thus, when the two vectors are parallel and in the same direction, then the magnitude of their dot products is maximum, as cos 0 degrees is equal to 1. Thus, we get I dot I equals 1, as shown. Similarly, we get J dot J and K dot K equal to 1 as shown. The angle between any two mutually perpendicular directions, that is, between I and J, or J and K, or K and I, is 90 degrees. And cos 90 degrees is 0. So, I dot J is equal to 0. J dot K is equal to 0. And K dot I is equal to 0. How can we find the dot product of a vector expressed in terms of its components along coordinate axis? If two vectors A and B are expressed in terms of their components along coordinate axis AX, AY, AZ, BX, BY, and BZ respectively, then A dot B is equal to AXI plus AYJ plus AZK dot BXI plus BYJ plus BZK, which is equal to AXI dot BXI plus BYJ plus BZK plus AYJ dot BXI plus BYJ plus BZK plus AZK dot BXI plus BYJ plus BZK equal to AXI dot BXI plus AXI dot BYJ plus AXI dot BZK plus AYJ dot BXI plus AYJ dot BYJ plus AYJ dot BZK plus AZK dot BXI plus AZK dot BYJ plus AZK dot BZK, which is equal to AXBX into I dot I plus AXBY into I dot J plus AXBZ into I dot K plus AYBX into J dot I plus AYBY into J dot J plus AYBZ into J dot K plus AZBX into K dot I plus AZBY into K dot J plus AZBZ into K dot K. Substituting the values of I dot I, J dot J and K dot K as 1 and the values of I dot J, I dot K, J dot I, J dot K, K dot I and K dot J as 0 and simplifying, we get A dot B is equal to AX BX plus AY BY plus AZ BZ. It is also equal to BX AX plus BY AY plus BZ AZ, which is equal to B dot A. As the dot product is commutative, A dot B equals B dot A. Now, using the dot product, we can measure the work done as the dot product of the force and displacement, which is equal to FD cos theta. However, the work done can be positive, negative, or zero depending on the values of the angle between the force and the displacement theta. The work done by a force is positive when the angle between force and displacement is acute. That is, the angle is less than 90 degrees. An example of this is when an apple falls freely towards the earth. The work done by the gravitational force on the apple is positive. In this case, the angle between the displacement of the apple and the gravitational force is 0. Similarly, when a spring is compressed, the work done by the compressing force is positive. In this case too, the angle between the direction of the applied force and displacement, which is the compression of the spring, is 0. The work done by a force is negative when the angle between force and displacement is obtuse. That is, greater than 90 degrees and less than or equal to 180 degrees. In the case of a rising balloon as shown, the work done by the force of gravity acting on the balloon is negative, since it is opposite to the displacement of the balloon. In the example of a boy lifting a stone, the work done by the gravitational force on the stone is negative, as the displacement is against the gravitational pull. The work done by a force is 0 when the force is perpendicular to the displacement. Consider a block moved over a horizontal surface. In this case, the displacement is along the horizontal, whereas the gravitational force, which is the weight of the block, acts vertically downwards. Here, work done by the gravitational force is 0, since it acts perpendicular to the displacement of the body. As another example, consider a stone tied to a string, whirled in a circular path. Here, a centripetal force acts on the stone to maintain its circular path. Centripetal force is always directed towards the center of the circular path, whereas the displacement of the stone for an infinitesimal time interval is along the tangent to the circle at the point under consideration. As the direction of the force is perpendicular to the displacement, the work done by a centripetal force is 0. The SI unit of work is joule, which is denoted by the letter J, named after the famous British scientist James Prescott Joule. Thus, 1 joule is defined as the work done on a body when a force of 1 Newton displaces the body in the direction of the force by 1 meter. Now you will learn about the relationship between work done on a body by a net force and the change in its kinetic energy by using the work-energy theorem. According to the work-energy theorem, the work done by a net force on an object is equal to the change in its kinetic energy. We know that the kinetic energy of a body of mass m moving with a velocity v is equal to half mv square. Consider a body of mass m moving with initial velocity u and let the constant net force F act on it. At the end of displacement d, its velocity becomes v. We know from the equations of motion that v square minus u square is equal to 2ad. Multiply both sides with half m and simplifying, we get the expression as shown. We get half mv square minus half mu square is equal to mad. On the left side of the equation, half mv square is the final kinetic energy of the body, and half mu square is the initial kinetic energy. On the right side of the equation, we have the product of m, a, and d. According to Newton's second law of motion, ma is the force on the body. We have on the right side product Fd, which is equal to the work done on the body. This proves that the work done by a constant net force is equal to the change in its kinetic energy.